Hi guys, we are going to look at session 17, okay, which is what we worked through last time. So if you look at 3A, that question asked us, all triangles are convex. Is that true or false? That is true. If you want to review the definition for convex, it is here at mathwords.com. It's a geometric figure with no indentations, okay? You might think of what does that mean? If every line segment connecting the interior points is entirely contained within the interior, most polygons are going to fit that description. Okay, so if I go back to my answer sheet here, part B says if the triangle has two acute angles, then it is an acute triangle. That's false. We have to have three acute angles. Otherwise, if we had the sum of two that's less than 90, it's possible that third could be greater than 90 because remember, we have to get up to 180. Part C, if we have a triangle with three sides of equal length, then it is isosceles. The definition of isosceles is two sides, so that's false. Three sides would be equilateral. Part D tells us some triangles do not have acute angles. That is false. We have to add up to be 180. So if we had three obtuse angles, if we have three measures, or even a right angle, if we have 90 or above three times, we're going to exceed the 180 needed for a triangle. So that's false. For part E, if a triangle has angles that are all different measures, then it is scalene. That's true. Remember, angles and sides have relationships. The largest angle is always opposite the largest side. The smallest angle is always opposite the smallest side. And that's true about equalities as well. If we have two equal angles, we'll have two equal sides, and they'll be opposite that. So this is true because different angles means that we also would have different side lengths. So true. When we go on to number 4, it asks us if we use a compass to make a triangle with the sides of lengths 1.5, 2, and 2.5, how do you know before you use your compass whether or not you can make it with these measurements? Okay, now my sketches are on another page. I don't know if I've uploaded them or not, but hopefully after you sketch this, or even before you sketch this, you should know you could do that because any two sides are going to be greater than the third. We could check that with basic addition. For part B, it says two students working on the in-class problem 1 wrote down the lengths 1 and 7/16, 1 and 3/8. What's a possible third length they can use? Now, again, there's a lot of different answers we could have here, but what would we know about that side? Okay. Any side, it's going to have to be less than 2 and 3/16 because when we add those together, 2 and 13/16, when we add those together, we get on those two sides, we have 2 and 13/16. So any side bigger than that won't work. Any side smaller than that would. Okay. So when we look at part C on that, what is the possible third length they can use so it won't create a triangle? Use it to show us why construction doesn't work. Any third side larger than 2 and 13/16 is not going to happen because of the reasons that we have discussed. Okay, so if we move on to question 8, okay, again, I'm going to zoom in just a little bit here so we can see this just a little bit plainer. And I'm going to expand my screen. Okay, it tells us, I don't know what's going on over here, but the question asks us to define a cube and what other solid names are also appropriate for cubes. A cube is a regular polygon for which all faces are square, okay? And we also could call it a quadrangular prism. Remember, prisms are named by their base, okay? So a cube is four-sided, which is where that quadrangular prism comes from. So part B asks us to find the volume of cube A, whose edges are 4 centimeters, cube B, whose edges will be 3 times that, and cube C, which will be 5 times that. So I just sort of sketch these. Now, I know they're not drawn to scale, but they're just a visual model. So we've got a 4 by 4 by 4, a 12 by 12 by 12, and a 20 by 20 by 20. 4, 3 times 4, and 5 times 4. So if you look underneath here, I did the calculation for the volume. Okay, we got 64 centimeters cubed, 1728 centimeters cubed, and 8,000 centimeters cubed. When we talk about the ratio here, remember that's just kind of comparing these by division. You could have set it up like I did here with a colon, or you could have written it as a fraction. Either way, okay? Basically, what we see is that edge ratios are not necessarily the same as volume ratios. Each edge increase happens in all three dimensions. Okay, so I get 3 times bigger this way, I get 3 times bigger this way, and I get 3 times bigger that way. And that's going to affect the volume by 3 cubed. 3 in this dimension, 3 in this dimension, 3 in this dimension, which is why we get a 1 to 27 ratio between these two things. Okay, when we look at A to C, we have 5 times bigger here, 5 times bigger here, and 5 times bigger here, which is why we get a ratio of 1 to 5 cubed. That's what 125 is, 5 times 5 times 5. When we look at D, we're sort of doing the same thing, but we're looking at surface area. Okay, so in cube A, I have 6 faces. All of the faces are square, so I have 6 times the length and the width, okay, which is 4, which is 96 centimeters squared. Same thing in B, only I've got 12 times 12, okay, instead of 6 times 6. So 864 centimeters squared. I'll have the same things here, 6 times 20 times 20, okay? So I'm going to go on to the next image so we can kind of continue this question. No matter what we do when we look at that, again, we're thinking about getting 3 times bigger and 5 times bigger, but we're talking about area now. So that's just in 2 dimensions. So that's why we get a 1 to 9 ratio here with the surface area, because 3 times bigger in 2 dimensions is 3 times 3, which is 9. We have a 1 to 9. And here, 5 times bigger in 2 dimensions, 5 times 5, which is 125. Okay, similar explanation to the volume. The difference is present in 2 dimensions since this is area. Okay, now we look down at part E. That is a false statement. Okay, and why? If the edges are doubled, so that means we're seeing twice as much. Okay, a double increase in all of the sides. Okay, we would have if we think about this as our original, okay, say we had 3, okay, and we doubled those, we would have 6 and 6. So we're getting twice as big in the surface area, we're getting twice as big in the volume. So we would have a difference of 4 times the amount, okay? Doubled would be 2 times 2. Doubled here would be 2 times 2 times 2 because we're going in 3 dimensions, okay? All right, moving on to that last segment, which is question 10. Okay. Question 10 specifically asks me to explain what these things mean, how they're similar and how they're different, and you could include pictures representing each one. So we talk about 4 inches. That represents length in units that are 1 inch each. This is a linear measurement. Okay, something could be 4 inches long, it could be 4 inches wide. We're really just talking about one particular dimension here. That's what linear means. Okay, so I drew a little example down here of something that's 4 units long. We're going to assume each square is an inch. Okay, 4 inches squared, that would be an area that is measured in inches times inches in squares. Okay, so we're going to look at this. I have 4 inches squared on the inside of this 2-dimensional figure. So I've got 2 inches times 2 inches. That's the 4 inches squared that's going to be on the inside. Okay, so a 2-dimensional measurement, that's area. Okay, 4 inches cubed represents volume measured in inches times inches times inches. So now we're talking about volume that can be held. This is cubic inches. So this would be a 3-dimensional object, which is a prism here. It's a rectangular prism. Sometimes we call these a box with elementary kids. It's a 1 by 1 by 4. Okay, so 1 tall, 1 wide, but 4 long, which would give us 4 cubic inches that would be held inside of that particular shape. We go on to question 11. We have sort of a present And I sketched it out here on my paper and included the measurements that the prompt gave me. It's a 15 by 10 by 4, okay? And I just threw those measurements in. It's really irrelevant kind of how we put them in, but ultimately we're going to be looking at the same total volume and surface area here. So if we think about the wrapping paper, remember that has to cover all of the surfaces of the present. So I know I'm dealing with surface area. When I think about surface area, I can't just say that this is 6 times the face because this is not a perfect cube, okay? Because it's not a perfect cube, all of my faces are going to be, not all of them, but some of them are going to be a little bit different in size. So if we're not dealing with a perfect cube, I kind of have to break these faces down differently. I might think of the surface area of the front and the back, the top and the bottom, and the left and the right. Usually because those faces are going to be mirror images of each other. The top and the bottom are going to be the same size, the left and the right are going to be the same size, and the front and the back are going to be the same size. Obviously, my drawing is not so great at conveying that, but your box wouldn't really look like a box, wouldn't look like a complete prism if that wasn't true, okay? So you'll notice here I've calculated volume by thinking about the front and the back, the top and the bottom, and the left and the right. And whatever amount I got, I doubled that because the front is going to be 40 units squared, and so is the back. So together I have 80 units squared. Okay, the front and the back, I'm looking at this face here, which is a 10 by 4. Okay, I've got that on the front and the back. The top and the bottom, okay, is going to be a 10 by 15. So I have 2 of those, which is 300 units squared. And then I have my left and the right, which is a 15 by 4. If you look at the size of that thing, okay, which is 60, and double those, I have 120 units squared. So 500 units squared, which I guess this is inches. It's 500 inches squared to cover the entire box, assuming there's no overlap. Okay. Now we think about the ribbon. Okay. The ribbon pretty much doesn't need to cover all of the faces. It just needs to wrap around the box. Okay. So if we were to sort of pretend that we were a little tiny microbe maybe, and we were walking across the outside perimeter of this box, okay, that's what we need to pretty much be able to do. So I started thinking about if I were wrapping a ribbon around this, how much would I need? Well, if I wanted to go across the front here, okay, it depends on how we're going to wrap the ribbon. We actually have to wrap it in both. So I may have to adjust my calculations for this as we go through because I'm not sure if I thought about that. If you look at the picture, you see that the ribbon wraps around the present from front to back, and it also wraps around the present from left to right. Okay, so before I look down at my calculations, let's kind of walk through this. So if I want to wrap the ribbon around this way, if I start at the bottom, I'm going to go up 4 inches. Then I have to go across 15 inches, back down 4 inches, and then back across 15 to get to the front. Okay, so I have 8 plus 30. That would be 38 inches of ribbon to go this way. Okay, now if I wanted to go this way, I would have to go up 4 inches, across 10, down 4, okay, and across another 10. So I would have 8 plus 20, which would be 28. So I have 38 and 28. Okay. So if I have 38 and I have 28, if I add those two together, that should be the total amount of ribbon that I would be using here. Okay. Which should be about 66 inches. If we add 2 feet for the bow, we got 90 inches of ribbon. So I think my calculation here is going to be wrong because I did not look at the picture when I did this. I just assumed that we only went this way, when in reality we went this way as well. So if you look at the picture in your course pack, you'll see that. So before I scan this answer key and put it up, I will correct that. But we're looking at wrapping the ribbon all the way around here. sort of going around it long ways and hamburger and hot dog style. Okay. So it also asks us for what would be the largest volume that we could be holding in this present. So if I kind of scroll down to this, if I look at length times width times height, because I do have a box here, I would be looking at 150 times 4, which should be about 600 inches cubed or 600 cubic inches. All right, after you have taken a look at this and corrected any work that you have to correct, you may want to visit the discussion board before you go on and look at session 18.